Hi students, today we are going to discuss the topic lens maker's formula. Now before going to this topic, let us see what we have studied in video 5, that is refraction through a spherical surface. Refraction through a convex spherical surface. Now, imagine we have a convex spherical surface, and this spherical surface separates a rarer medium of refractive index mu1 from a denser medium of refractive index mu2, and an object is placed along the principal axis at point O, and the ray after get incident on the spherical surface get refracted, and a final image was obtained at I. And using this video or using this derivation, we found out the relation between the object distance u, image distance v, radius of curvature r, and refractive index of the medium. And we got the equation as mu2 by v minus mu1 by u is equal to mu2 minus mu1 divided by r. This was the equation which we obtained using the derivation of refraction through a convex spherical surface. The same equation you will get if you are deriving for a concave spherical surface. Now, in this video, we are going to discuss about lens maker's formula. From the name itself, you can say lens maker's formula. This is the formula or equation used by the opticians or the people who make lens to make the lens. Okay. Now, this formula relates the focal length of the lens to the refractive index and radii of curvature. So, lens maker's formula is an equation which relates the focal length, refractive index and radii of curvature of the lens. Sometimes you will not be asked the question, what is lens maker's formula? You will be asked to derive an equation which relates the focal length, refractive index and radii of curvature of the lens. So, you have to use this particular derivation. Okay. Now, imagine you have a convex lens . And an object is optic center, okay, and an object is placed beyond the focus of the lens, somewhere here. What happens? A ray of light from the object get incidence on the lens, from where it get refracted, reaches the other side of the lens, again it get refracted and a final image is obtained, which is the real image. Now, for deriving the lens maker's formula, what we do is, we divide the lens vertically into two sections. Okay, one is a convex surface which separates the rarer medium having refractive index mu1 from the denser medium having refractive index mu2, and using the equation of the one used to derive the and using the equation of refraction through a convex surface, we will derive an equation. Then we will formulate one more equation in which the image is formed by the next refracting surface at point I. Now, what happens is that what we do is, we keep the object in front of the first refracting surface, and this refracting surface forms an image at somewhat at I1. Now, these two are not very far away, okay, it's just an assumption for deriving the equation. Now, this image is actually a real image. and this image acts as a virtual object, means an imaginary object which we will not be seeing, which acts as a virtual object for the second refracting surface, and the second refracting surface produces the final image at I. So, I is the final image, but when we use a lens, we will just see the object and the image, but when we are deriving this equation, we are deriving this method, the first refracting surface forms an image I1, which will be that will be a real image actually, but it acts as a virtual object, means the imaginary object for the second refractive surface. And the second refractive surface using that object forms the final image I. This is how we derive this equation. Now, like we use certain assumptions for deriving the refraction through a convex spherical surface, here also 4 assumptions are used. The first one is assumptions. So, these 4 points are very important for the board exam, because they will ask the question which are the assumptions used for deriving the lens maker's formula. So, the first assumption is the object is considered to be a point object. The object is a point object. Okay. The second assumption that we take is the lens is very thin. You are using a very thin lens. You are having one comparatively larger focal length. The third assumption used is the aperture, that is the diameter of the lens is small. You are using a lens of small aperture. And the final assumption that we use for deriving this equation is the rays are paraxial. Now, in optics, we basically use 2 different types of rays. One is the marginal ray, and second one is the paraxial rays. When you read the books, you will read these 2 terms, marginal rays and paraxial rays. Now, marginal rays means the rays which are far away, or rays which enter the lens at the edges. These are the marginal rays. And paraxial rays means the rays which are very close to the principal axis. The rays which are very close to the principal axis are known by the name paraxial rays, and these rays make very small angle with the principal axis, so that sin theta, tan theta can be approximated to theta itself. Okay, so paraxial rays means the rays which are very close to the principal axis and which make small angles with the principal axis, so that we can approximate angle of sin and tan to the angle itself. Now, this is the diagram used for deriving the lens maker's formula. Okay, so we have a lens ABCD, ADC, which are the 2 refracting surfaces, and the lens is having a refractive index mu2 displaced in a medium of refractive index mu1. Okay, now an object O is placed in front of the spherical surface ABC. So what happens? The ray from O incident on the spherical surface ABC at point M, from where it gets refracted along the path MN and reaches the next refracting surface ADC, from where it again gets refracted and final image is obtained at point I. Now, as I told you in the beginning of this video, what happens is here the first refracting surface forms an imaginary image at I1, and this I1 acts as what? It acts as a virtual object for the second refracting surface ADC, and after refraction we obtain the final image at I. We only see the object and the final image. We won't be able to see the real or virtual object created by ABC. Okay. So, we just formulate 2 sets of equation and we add the equation and we will find the what is the final equation for lens maker's formula. It's a very simple derivation. So first what we are doing is we are going to consider the first refracting surface A, B, C. This surface. Now if you look into the surface, you can see the object is placed at point O. So U is the object distance. Okay, and the image is obtained where? Image is obtained at I1. So V1, we are taking it as the image distance. So here the object distance is U. Image distance is V1, not V. And also if you take the lens, the part of this surface is a part of a sphere, is having a center of curvature C1. So its radius of curvature is R1. So radius of curvature for the refracting surface ABC is take it as R1. Now using these variables, we will formulate an equation by substituting it in the equation for the one which we obtained used for a convex spherical surface. What was that equation? It is mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. This was the equation which we obtained for a convex spherical surface in the previous video. Same equation we are using, and we are going to substitute the value for image distance, object distance and radius of curvature. So what will be our equation? Our equation will be mu2 by V. Here what is V? It is V1, image distance, minus mu1 by object distance. Here also it is U, is equal to mu2 minus mu1 divided by R1. Now this is the equation 1, which relates the image distance, object distance and radius of curvature for the first refracting surface A, B and C. Okay. Now next, what is our step? Next, so we got an image at I1. This image is acting as what? It is acting as an object for the next refracting surface A, D, C. And we are getting the final image at I1. Sorry, I. So here, if you look into this diagram, you can see this case V1 is the object distance and V is the image distance. And also for this spherical surface A, D, C, the sphere is to this side. So center of curvature is here, C2. So radius of curvature will be R2. Okay. So for the second refracting surface, for the refracting surface A, D, C, the object distance is what? The object distance is what is now V1, because I1 is acting as the virtual object for the second refracting surface. Image distance, that is the final image obtained, is V. Radius of curvature is R. Is R2. And one more thing which you have to remember is, see, for the first refracting surface, the object was kept at point O. So in the refractive index of medium mu1, and the image was formed, it's an imaginary concept, in the second surface, that is having refractive index mu2. But now what is the next concept we are taking? We are taking the second refractive index, second refracting surface. So the object is assumed to be in the refractive index of medium mu2 and the image is formed at the refractive index of medium mu1. which means in this case, object is placed, that's just an assumption, okay, the refractive index having, in the medium having refractive index mu2, and the image is formed in the medium having refractive index mu1, which means when you are substituting, don't get confused. So, use substituting the values in the equation for refraction through a spherical surface, we get, what was the equation? Mu2 by V. Here it becomes mu1 by V, because the final image is obtained at mu1 minus mu2 by, what is the object distance we are taking? It is V1 is equal to mu2 minus mu1 by R becomes mu1 minus mu2 divided by R. Now this is equation 2. Now what is the next step? The next step we are going to do, add equation 1 and 2. So adding equation 1 and 2 gives mu2 by V1 minus mu1 by U plus, right hand side and left hand side we are adding mu1 by V minus, mu2 by V1 is equal to mu2 minus mu1 by R1 plus mu1 minus mu2 divided by R. This and this will get cancelled. If you take mu1 outside, you will get 1 by V minus 1 by U is equal to, I am going to take mu2 minus mu1 outside as common. So, I will get mu2 minus mu1 into 1 by R1 minus, why minus? Because here it is mu1 minus mu2 by 1 by R. Or I am going to take mu1 to the other side, I will get the equation as 1 by V minus 1 by U equal to mu2 minus mu1 by mu1 into 1 by R1 minus 1 by R2. Okay. Now, if we imagine the object to be placed at infinity, you have studied the ray diagram, sentence standard, isn't it? If the object is at infinity, then the image is formed at focus, which means if U is at infinity, we will get V at the focus. So, the above equation can be written as 1 by F minus 1 by infinity is equal to mu2 minus mu1 divided by R divided by mu1 into 1 by R1 minus 1 by R2, and 1 by infinity is 0. So, the equation becomes 1 by F is equal to mu2 minus mu1 by mu1 into 1 by R1 minus 1 by R2. Now, this is the lens maker's formula which relates the focal length with refractive index and radii of curvature of the lens. Now, imagine special condition if we are keeping the lens in air. Okay, if the lens is kept in air, you all know refractive index of air is 1. So, mu1 becomes equal to 1 and mu2 can be written in general as mu. So, the equation can be written as 1 by F is equal to mu minus 1 by 1 into 1 by R1 minus 1 by R2. I hope you understood this derivation. It's a very simple derivation. We are just considering two spherical surfaces formulating the equation for image, object distance, refractive index and radius of curvature for each spherical surface. Then we are adding the equation and just assuming if the object is formed at infinity, the image will be formed at focus. Rearranging the equation, we will get an equation relating the focal length, refractive index and radii of curvature. And it's known by the name lens maker's formula. Thank you.